In this video, we'll look at integrating with polar coordinates. We'll answer the question, why do we get that extra r in the differential? And we'll do an example called the napkin ring example. So to begin, we'll look at the general problem of integrating some function of two variables with respect to some differential in area over some region D in the two-dimensional plane. Here's a picture of the scenario that we are analyzing. The function f is defined on x and y, so of course I would have an x-axis here, a y-axis here, and the function f is defined on this region D, but it could happen that the region is such that it'll lend itself to polar coordinates better than rectangular coordinates. So if the region is expressed in polar form, as it is here, where we have the components r and theta, r being a radius from the origin, theta being some angle, if that angle is in the interval from alpha to beta, so you can see here is theta equal to alpha is one boundary of the region, and this beta is a constant here, is another constant boundary of the region. But the r values can in this region can vary depending on the angle. You can get different r values, and that's why I have sort of curvy boundaries here that can change a smaller radius and a bigger, larger radius as the angle changes from alpha to beta. So a region that's defined or that can be expressed in this form, we can convert that general expression for the integration of a function over a region, we can convert into a polar form in this way. Notice that the alpha beta are the outer bounds in this expression. Outer bounds are values of theta, and the inner bounds are r values that change with the angle theta. And what's meant here is that wherever there was an x in the original function, you have to replace it with the polar form for the value of x, which is some r value times cosine of theta for the location of that position. And you're just converting into polar. All the rectangular coordinates are being converted into polar, and that's what all this is. And one of the first things that you recognize in the polar form is there's this extra factor of r right here that comes along with this conversion into polar form. And you could absolutely wonder, like, why is that r there? It's supposed to always be there when we're in polar. So let's see if we can figure out why that r is there. Another thing that I want to comment on as far as this region is, for this region D to actually be a region in the two-dimensional plane, then I'm going to expect always beta minus alpha to be positive, for one thing, or not zero. I mean, not negative, and to always be at the greatest equal to 2 pi, because if the difference in these angles was greater than 2 pi, we have a region that's sort of overlapping on itself in the difference between the two angles. And so I'm going to put that restriction on the possible values of alpha and beta, that the difference is not a negative and it is less than 2 pi, and only in that circumstance would I actually have a region in the plane. Another thing that I want to include here is that h2 as a function of theta is continually greater than h1. It's measuring a radius, a distance from the origin. So I want h2 to be the outer bound and h1 to be the inner boundary of this region D, and I want these boundaries to always be non-negative as well, to correspond to some simple region in the plane. Now, before I go a little bit further in exploring where this r comes from, I want to talk about two different scenarios that can occur with respect to these kinds of regions that we can put in polar form. So there's the first region that is called an r simple region in the figure here. This region has fixed bounds for theta. So the theta, it's a region that has constant boundaries at different angles, right? The alpha and beta form constant boundaries for the region. And the boundaries that aren't constant are the R values, how the radius can differ as you change the angle from the initial alpha to beta. You can see this curve changing. This is where we have the function g1 that depends on the angle, and here's some other boundary that's formed by some function g2 that changes with the angle. So this is the R simple region, and maybe we can associate R simple with an integration in which we do R first. We would think of it as a particular angle theta. Maybe I'll highlight it like this. If I chose a particular angle theta, then at that point the integration is happening from one R value to another R value for a specific angle in the interval. So in fact, we could say, just starting at alpha we integrate from g1 to g2 at that particular angle. And so we're doing the integration with respect to R with a fixed angle theta. And then we do that for every angle from theta equal alpha to theta equal beta. That's one possible type of polar region that we can handle with the double integral. And the other one is a region that is like this sort of theta simple region. And what we have there is variable bounds for the theta. So the angle actually depends on how far you are from the origin. So depending on your R position, you'll have a changing theta, right? Could be a larger angle of theta or smaller. The angle changes as we change the radius, right? So that's what the variable bound for theta represents. And then there are fixed constant boundaries at one radius R1 and another radius R2. So this is when we call theta simple. We might say that the theta simple region is one where we sort of do the integration with respect to theta first, and then the integration with respect to R, because either the region, it's easier that way, or because it's easier to do that way in the actual integration. It's probably because of the region, I would think, that you would set it up like this, but you can imagine that you're actually maybe picking one particular R value somewhere, like maybe this value of R, and holding that constant, and then integrating from one theta value to another theta value for that constant R. And so we're actually sweeping out the region sort of in this way, because what I'm thinking is you pick an R value and then you integrate along theta in this scenario, where back in this one we were picking an angle and then integrating along the R values. So we're filling the region sort of in this way, in the R simple. We're filling the region, we're like say covering the region sort of in this way for the theta simple type of region. Okay, it doesn't matter whether you have a R simple or a theta simple, you still have this R d theta dr, or maybe it's an R dr d theta, and actually it's the order here that really matters, whether you have one region or the other. But in both of these forms, I have this extra factor of R that gets included as part of the integrand, included as a product. We multiply R times whatever this polar function is. We multiply R times that, and then have these differentials where we integrate with respect to R, and then theta. In this case, here we would multiply R times whatever formula happens to be here, and then we integrate with respect to theta, and then finally integrate with respect to R at the end. So we still get this factor of R. It doesn't matter what order of integration we do this. So again, the question that I'm going to address is, where does that R come from? Why does it have to be there? Why is that there? So let's go through that. So then let's move now to a sector of a circle. This shaded region here is a sector of a circle, and its area is given by this 1/2 r squared theta, where r is the radius and theta is this angle that forms the sector. And just to, it's pretty quick to see where this formula comes from. It's a kind of neat thing to see. Let's begin with, if you had a whole circle, the entire circle's area would be pi r squared. And if the angle was in degrees, I could put theta over 360 to get that fraction of the circle. I would multiply by a fraction. For example, if the angle was 180, you'd have exactly half of the circle. And if the angle was 90, you'd have 1/4 of the circle's area. But if I want the angle to actually be in radians, I have to convert it to degrees in order to apply this formula. So let's move this pi r squared over. So what we could do is say that if the angle was meant to be in radians, we'd have to convert it to degrees so that this formula would work. We'd convert it to degrees by multiplying by 180 over pi, and that's, now the pi's cancel, 180 cancels with 360, and this is where I get this formula, 1/2 times the r squared times the theta, and that's what you see there. So that's this shaded area. So finding the area of this shaded region here will be just the difference between the areas of two polar sectors, or two sectors of a circle. First, I'll point out that I'm choosing to name the angle here between beta and alpha. That beta minus alpha is itself an angle. I'm calling that delta theta here for obviously where this is headed later, but it's just an angle. I could have also just called it theta. It was the same theta that we had just previously in this picture here. That angle theta, the area for this sector, is 1/2 r squared theta, and I'm using the same thing, but I'm just going to call the angle here, this angle is delta theta. And so the area that's shaded is the larger polar sector area minus the smaller polar sector area that has this radius of 1. So if we take the entire thing with a radius of 2, it's almost like the whole piece of pizza, and we subtract off this little piece of pizza, then we have this shaded region left over. That's the difference in these two areas. But what I want to do from there is recognize both of these terms have a 1/2 delta theta factor in each term. I'll factor that out in front. I'm left with an r2 squared minus r1 squared, which, because it's a difference of squares, it'll factor like this. And then the interesting thing that happens here is that we can shuffle these factors around. Put this r1 plus r2 with the factor of 1/2 so that the 2 moves underneath. Just slide the 2 underneath, or slide this guy over and put it on top of the 2. Slide the delta theta to the end and put the r2 minus r1 as a factor that appears here. And then imagine now if the r2 and r1 get closer and closer together. This will be what we could call a delta r. And we'll imagine that delta r getting smaller and smaller, and the delta theta getting smaller and smaller. And so this little polar region is going to be smaller and smaller and smaller, and it'll become a differential amount of area. And so that's exactly what happens as the delta theta approaches 0. As it goes to 0, and the differential in r, as this differential in r, as it approaches 0, as it gets smaller and smaller, what happens is we find a smaller and smaller differential amount of area. So the region becomes a differential in the area as this delta theta becomes smaller and the delta r becomes smaller. And as that happens, this you can interpret as an average value of the two r's, right? It would be maybe right about there. If you take r1 and r2, add them together, divide by 2, you're getting a value that converges to a single number as the r1 and r2 get closer and closer to each other. So in the limit of smaller and smaller delta r's, R1 and R2 approach the same value. And so this approaches just a single point that we could rename as just R. So this differential amount of area, that becomes R, this becomes dr, and this becomes delta theta in this limit of smaller and smaller differential, smaller and smaller changes in area that approach a differential in area. So the area is, in polar form, is becoming this product of three different factors. Another picture of what's going on there is that some region in the two-dimensional plane I'm dividing up into little sectors that I want to evaluate the function at each of these points. And so as my small incremental amount of area becomes a differential in area, as that happens, that region that we could call R sub ij, that's one of these ultimately infinitely many. There's a finite number at first, but as they get smaller and smaller, it becomes an infinite number of these little polar regions. In that limit, well, first of all, the actual area, just as we derived above, is the two different radiuses added and divided by 2, the difference of the radiuses and the difference in the angles for that particular region. And as I was just saying, as you make each of these smaller, as we increase the number of these little regions, this will approach R, this approaches a differential in the radius, and this approaches a differential in the angle. So the area becomes R dr d theta. So that's some background as to where the R comes from. And there's one other little way to reason out why is a differential in the area equal to R dr d theta, or as another option, this product. And you could see it like this. If you remember from very beginning of trigonometry, that for any angle theta, there is an arc for this sector that we could call S that could be determined. The length of this arc is based on the radius times the angle. That's really where radians comes from. And so if the actual angle wasn't theta, but it was d theta, some differential amount of angle, you could say that arc right there is a length that is r d theta, and if you multiply that by dr, then you're approximating an area of a sort of polar rectangle. This could be sort of like a width, and this could be a length. And so that's another way to see it sort of intuitively happening, that the differential amount of area is this product, one side of the polar sector times another, r d theta times dr. So let's move on to an application of these polar coordinates and double integration. Let's do the napkin ring problem. So the napkin ring problem is this question of finding the volume that's left over when you begin with a sphere but drill a cylinder through the sphere. What's the remaining volume? The volume of this red solid here, it's the volume that you would get by taking these yellow regions and rotating them through three-dimensional space around this sphere, where a portion of the sphere has been just drilled out, so it's no longer there. So was a sphere, cylinder is drilled through it. What's the remaining volume? The amazing thing about the napkin ring, and I already have a video on this for Calc 2 where we don't do double integrals. We could do this again now with double integrals and polar integration, and we'll get the same answer. But what was so striking about that is that as long as the heights were the same in any two of these napkin rings, as long as the height where the height was this distance here, as long as that was the same, you could have completely different spheres that is, the larger radius, the radius of the sphere, could be completely different from one napkin ring to another. And also, the radius of the cylinder that you drill through that sphere, completely different in one napkin ring and the other. But the volumes of the resulting napkin rings are going to be exactly the same, so long as the heights remain the same in each of them, which is like just weird that the volume seems like, obviously, of course it does depend on the larger and smaller radius, but it can be determined if you know just the height. So you can do a little trick of Pythagorean theorem at the very end to say that actually this R1 and this R1, these guys are related to this side H, and so we can directly relate the total volume of the napkin ring simply to a value that measures the height, and actually that means that these volumes would come out the same, even if the radiuses were different. It's amazing. So here's another picture of this situation that we're going to apply our integration. We're going to find the volume when this region, which is outside of the cylinder, this region that's shaded here, this is an h over 2 that's referring to half of the height of the cylinder. And I'll come back to that later. But right now I just need to recognize it's this shaded region that's getting rotated around the y-axis that forms the volume that we're trying to calculate, the volume of the napkin ring. And we did that with shell method in Calc 2. But now I want to do a different way. It's always beautiful to see different methods producing the exact same result, so that all of these ideas are all consistent. That's a neat thing to see also. So just to compare these two really different methods give the same results, a satisfying thing in and of itself. So, but we'll now do it with polar coordinates and double integrals. And so what we need to do is to figure out the region on which we're going to integrate. And since that region has this kind of shape, you see this big R is the radius of the sphere. You have to now imagine a z-axis coming out of the screen toward you that puts this into three-dimensional space, so that there's a sphere with a radius of r living in that three-dimensional space, and through that sphere, drilled right down through from the top all the way through it, we're drilling out this cylinder that has a radius little r, and we're figuring the volume of that sphere that remains when this is like a core that's drilled out through the sphere. So this is the region that I want to set up for my integration, and so I want to put that region in polar coordinates because it's circle, so it's easy to put into polar coordinates. So we'll say r and theta. Now I could just do one quadrant, and it's perfectly symmetric. So if we integrate it just from 0 to pi over 2, that'll work perfect. I think that what I'll do here is say that actually D is really the whole entire thing. Looks like a donut. So D is this whole entire donut, flat two-dimensional region though. It would be, let's say an R. Well, I think what I need to do is, if I want to use R as a variable, I'm going to use this little r as like, I'll go R0 as the radius of the cylinder, and then I can use R as a variable that goes from R0 to big R. So these R's are between R0, begins there, and goes all the way up to capital R, and the corresponding possible values of theta that determine this region I'll take from 0 all the way to 2 pi. So theta for this entire region ranges between 0 and 2 pi. So that's the region on which I'm going to do the integration. And the function that I want, well, the function that we're going to integrate on this shaded region is in the z scale defined above and below this region. So if we're going to write it as a function, we need to just take only the positive z values and then double the answer to get volume. So it'll be very much like in this picture here, where remember R0 I've now named as the radius of the cylinder, and I'm going to need to describe this sphere as a surface in three-dimensional space. Really, I had to take out that equation that defines that boundary, because that was y as a function of x in a two-dimensional graph where I just had the curve. But if I really want to describe the actual sphere, then let's make the z-axis vertical, an x-axis that could go out this way. Actually, I'd have to have a y-axis going, sort of positive y-axis going back into the screen, and the negative y coming out. Anyway, the equation for the sphere in three-dimensional space is x squared plus y squared plus z squared equal to whatever the radius of the sphere is. So it's from here that I can find a formula for the height of the sphere, the surface of the sphere. I can create a function where I get the z value as a function of the x and y by just solving for z. Of course, there'd be two possible z values, above the xy plane and below the xy plane. I'll just take the positive, and then I'll double my answer to get the total volume of the sphere. So I'm looking at this picture now. This is the sphere with the equation x squared plus y squared plus z squared equals whatever radius we want. This radius is a constant. If we solve for z, we've got z squared equals constant radius minus x squared minus y squared, and then solving for z to write a function, we have plus and minus square root, and it looks like that. So let's make our function a function of x and y, so that you get heights on the surface of the sphere, points on the surface of the sphere depending on x and y, by just choosing the positive z. So that's the function that I'm going to integrate, and this is a portion of that region that I had above. This shaded donut shape here, we're getting 1/4. We can see 1/4 of it here in the first octant, in the region where x and y are both positive. So I'm going to integrate this height, which would give me different points, different z values on this surface of the sphere. I'm going to integrate that for all the points in this region D. So finding volume, I can integrate over region D some function of x and y with respect to the area of that region. And since the region D is easily defined in polar coordinates, we'll do that. We'll go from starting at theta equals 0 to theta equal 2 pi. So I'm doing an R simple region, putting theta on as the outer bounds of my integration, and really integrating first inside with respect to R first. So as we choose fixed angles of theta, starting at 0, we fix 0 radians, 1 radian, 2 radians, 3 up to 2 pi radians. For each of those fixed angles, we integrate from one R value to another with that fixed theta. So this will be from R equal R0 to R equal big R, the outer boundary of the region D. This function, which I need to convert into polar, R is a constant in any coordinate system, but this x becomes R cos theta, and the y becomes R sine theta. And the y is squared. And then, because it's converted into polar coordinates, I get this extra factor of R that comes along with the polar form of a double integral. And because I'm doing R simple, I have R as the inner bound, so I have a differential in R first, and then a differential in theta to match this outer boundary of theta values. Now, this would just be the volume that is exterior to the cylinder. It's the volume of the sphere above the xy plane. So it's half of the volume of the napkin ring. Right? It's exterior to the cylinder and above the xy plane within the sphere. So the volume of the napkin ring is 2 times this integral that I have here. It's 2 because I'm only getting positive z values. I have to double the answer to include the total volume that would be completely the same, symmetrically, due to the symmetry of the sphere. It's exactly the same below the xy plane as it above the xy plane. So to get the full volume, I just double my answer that I get here. Okay, so I don't know how much time is remaining in this video, but will I have enough time in the time remaining to actually figure out? This looks pretty daunting, but I think it's going to simplify really quick. I can see a couple things that are going to happen right away. So let's go 0, 2 pi, r0, and r, and square root. You know, I'm going to factor out the r squared. I'll factor out a negative r squared, so that I get cosine squared theta plus sine squared theta inside here. R dr d theta. Because I'm going to take advantage of this equaling to 1. So let's move this to the next page. Okay, and then what's going to happen here is a substitution. Let's take, because I happen to have this extra factor of r, that's just beautiful because this is an r squared and the derivative is 2r, and that'll work perfectly. The integration is just a u substitution. Let's go u equal big R squared minus little r squared. So the differential in u, what I need to do is get rid of the differential in r and replace it with a differential in u if I change the variable. Right now the variable of integration is r. I'm doing this iterated integration where we integrate with respect to r first inside for a fixed theta, right? So I want to get rid of this differential in r. I'm not worried at all about the d theta. That can come later. And I know that the big R is a constant in the integration with respect to this little r. So changing out the differential in little r to a differential in u, I take a derivative with respect to that little r. So that guy's a constant, and this is minus 2r dr. So I can replace the r dr with du over negative 2. Now, this is going to have to change the bounds when r, this is an r value, when r is r0, then the u is big R minus r0 squared. Big R squared minus r0 squared. That's the value that I get for u, and when r is big R, what will the u value be? It's big R squared minus big R squared. When this becomes big R, this is r squared minus big R squared. It's going to be 0, so this is just 0. Then I have the square root. I'm going to replace this with u. I'm going to replace the r dr with du over negative 2. And then I'll save that differential in theta for later when I integrate the last integral. So here's a couple of fancy things. First of all, that 2, being a constant, can come out of this integral, and being a constant in this outer integral, it can bring it all the way out past both of those integral signs. So the 2's are going to cancel. Another neat little thing is that I happen to have a negative here, and I notice that the upper bound is 0 and the lower bound is some positive value. So I'm going to flip the bounds and get rid of the negative and cancel the 2's. So all in one step. This is from theta equals 0 to theta equal 2 pi, u equals 0 to u equal this big R squared minus r0 squared. The 2's are going to cancel. And the negative is gone because the bounds switch. That's where that goes. So now this inner integral can now be evaluated because we have a antiderivative. We have an integrand in terms of u and a differential in u. So this is u to the 1/2. And finding an antiderivative by the power rule, that's u to the 3/2. I just took 1/2 and added 1. I get 3/2. If I divide by 3/2, I'll just change it to a multiply by 2/3. I have bounds u equal to 0 and u equal to big R squared minus R0 squared. And after I plug in the bounds, then I have some expression that I would integrate with respect to theta. Well, the constant occurs in both terms of the subtraction, so I could just factor it out. Just say the 2/3. In fact, you could take all the way out of the integral. 0 to 2 pi. I'm going to get this plugged in for u, R squared minus R0 squared to the 3/2 power minus, you would plug in 0, but of course that's 0. So then it just becomes that. Plugging in 0 just doesn't give me any other terms. And now this actually has no thetas in it, so this is all constant in the last integration, which means I could just say this constant times the length of the interval, so it's just times 2 pi. So we get 2/3 times big R squared minus R0 squared to the 3/2 power times 2 pi, because that's the length of the interval. Of course, you could also say it's this thing times theta is the antiderivative. Then you plug in 2 pi and you plug in 0, and you end up with the same thing. So 2 pi times the 2/3, we can go 4/3 pi, and then big R squared minus R0 squared with a 3/2 power. And this is a point that you could put a box around and say that's the volume. You can look at near to the end of the other video on the napkin ring, and there was a point in the process where I had exactly this expression. And then what was so special about the napkin ring is that you could go one step further and relate this to the value of h. So it is kind of hard to see in three-dimensional space, but there's my sphere, and I've drilled through a cylinder through the center of the sphere, and I can say that the big R is the radius of the sphere. And so you could draw it from here out, but if I draw it here, you can see a triangle that's useful for this last little step. So here's the radius of the sphere, here's R0, the radius of the cylinder, and this thing right now I'm going to call h over 2, where h is the entire height of the cylinder. And so that becomes a right triangle right there, and we could say R0 squared plus the quantity h over 2 squared is this hypotenuse of the triangle, big R squared. So then h over 2 squared is big R squared minus R0 squared. And so I can just continue with my formula for the volume and just replace this relationship between the radius of the sphere and the radius of the cylinder with this quantity h over 2 squared. Let's substitute that in. So the volume is 4/3 pi with h over 2 first squared and then raised to, that was a 3/2 power we had right there. 3/2 power. Well, that means that the 3/2 times the 2 gives me a cube. So I'll have 4 over 3 pi, and then I'll get h over 2 just cubed, right, because the 2's cancel. So this becomes an 8 in the denominator, 2 cubed. We'll say 4/3 pi h cubed over 8. So that's 4 over 24. Let's do it that way. So it's pi over 6 h cubed. So that was it. That was the formula that I got previously for the volume of any napkin ring. If you could relate the radius of the sphere, r, big R, and the radius of the cylinder, r0, with some height h, then it doesn't matter how big the sphere is, and it doesn't matter how large or small the cylinder is that you drill through it, as long as the height remains the same, you would have the same volume. This volume can be written only depending on the height of that cylinder that results. The height, which isn't the same as the radius of the sphere, right? Because you're lopping off a part of that sphere there. You have a height. You can go back to the picture here and see that the h, which would be here, this is the h that we just measured. That h is not the same as the radius of the sphere, right? Or even the diameter, right? The diameter is different than this height, and so it depends on that actual height, which we figured out based on these r radiuses. The radius of the sphere and the radius of the cylinder determine this h value, and so it's the h value alone that could tell you that volume. Okay, so that's it. That's the volume of the napkin ring using polar coordinates. Okay, that's the end of the video.